Now we have the data ready by counting those words, and let's have a look at how the email classifier works. The rules of classifying the messages based on those data features looks very stunning. Let's have a look at those rules more carefully. At first, we consider if the text has the word, the literal word text appear more than 0.5 times. That means whether it appears at all. Having split the data into two parts, we further investigate each of the parts by examining whether the term PM appears or the word forwarded appears. Go so on and so forth until we reach the conclusion whether the message is a spam message or a genuine one. So this is of course a decision tree. Let's have a recap of the decision trees. The decision trees is a very widely used and practical machine learning methods, and the trees are built from the training data to describe the relationship of the observable attributes in the data with the target values. A good point of decision trees is the trees are not very particular to the type of the data. They can work with mixture types of attributes. Of course, the tree we just have demoed is a tree based on the word count, which are numbers, but trees can also work with categorical data or binary attributes. When a tree has been built and works with data, the way a tree works is often interpretable. That is not necessarily mean that it is meaningful. For example, I do not know why the decision tree has decided to look for the word text first, but at least we can more or less interpret how the tree is working with the data. That is different from those black box models such as neural networks. Also, when trees are built, they are efficient to run. In the following, we consider constructing decision trees using one of its original methods, that is the ID3 algorithm. That algorithm constructs trees from top down. That is, first we consider the entire dataset and find an attribute according to which we will separate the dataset. We test for each of the instances in the observed data and compare the attribute with the target or the target of a prediction. Find the most related attribute, and that attribute will be tested at the root node of the tree. After testing the attribute at the root, we can group the training data into different subsets. In each of the subsets, we create a descendant of the tree. In each descendant node, we will recursively iterate the above discussed procedure, so on and so forth until we arrive at some node that all training samples in that node belongs to the same target class, and that finalizes the construction of the tree. Have a concrete example on how this algorithm works. Consider this data of the table. It is a table on which, for example, some sport committee to decide whether a game will carrying on or not. It mainly considering the weather. Okay, have a look at the data. The first step of constructing the tree is to choose an attribute at the root of the tree to test. So then for each of the attributes, we compare the relationship between these observable attributes, that means an attribute with respect to the weather condition, with the target value, that is whether to play or not. We quantize this relationship and choose the most related attribute to test at the root of the tree. Now we have the root of the tree, and for the root attribute, that's the attribute at the root of the tree, we have the three possible values. In this case, they are sunny, overcast, or rainy. For each of the possible values, we consider the corresponding samples. For the sunny days, for example, have a look at the sunny days. Take all the sunny samples out. We have only these 5 samples left. Okay. For these 5 samples, we choose from the other attributes, the next attributes to test. In this case, we may find, okay, the humidity is the very indicator. If the humidity is high, we don't play, and if the humidity is low, normal, we play. So the tree arrives to this descendant. The tree for this descendant will be based on humidity, and after testing the humidity, will arrive the conclusion of the tree. The second possible value of the root attribute is when the outlook is overcast. This is very simple because we found that it happens that for all overcast days, the game was carrying on. So if the value of the outlook is overcast, we directly arrive at our conclusion as yes. And following the same set of rules, we can conclude a scheme of we can construct a scheme of deciding whether to play the game or not. Okay. The next question to ask is how to assess the relation between an attribute with respect to the target value to predict. When construct each node of the decision trees, we need to choose the most appropriate attribute to test, and to which criterion we should choose an attribute over the others. We need a concept called information gain. That is, how well a given attribute can be used to separate the examples with respect to their target values. That means if we group the examples in our hands with respect to the values of a particular attribute, in those subgroups, how well we have done to organize the target values into those subgroups. An alternative understanding is that which question or the question about which attribute should we ask, so that the answer to this question is mostly related to the ultimately interested answer, that is the target value. Obviously, to measure the information we have gained from the operation of testing an attribute and answering the question, we need to be able to measure the information before and after that operation. So we introduced the concept of entropy, which measures information. Like if we are to measure distance, we will need meters, or if we are to measure weight, we will use some unit of grams. To measure information, the unit is bits. Intuitively thinking, bits represents the number of simplest possible questions, that is yes or no questions, one needs to answer to get rid of all the uncertainty in a system. And this number of yes and no questions, so-called bits, represent the information contained in that uncertain system. Entropy is a concept that comes from the information theory, and it has a deep connection with modern physics and cosmological physics particularly, and statistical dynamics. Actually, as long as modern science is concerned, the concept time is closely related to the entropy of the entire universe as a system. Entropy measures the impurity or chaos or disorder in a system, which makes sense if you think about that. Given time, when the system evolves with time, it always goes from some ordered state to some disordered state, and it also goes from pure system to impure system. And if the system there is more impurity or disorder in the system, you need more questions to be answered to get complete certainty with that system. So that is entropy measures the information, or we can see the lack of it. Let the system as a black box containing m things or objects. Each of these objects has a chance of being the outcome of the random experiment with a certain chance. This is the definition of the entropy of that system. Let us first try to understand those terms in this definition, and later we will come back to consider deeply that why the information is measured in this way. That is to take the sum over all of the things and let the pi be the corresponding chance that thing or that object to be the outcome of the random experiment, and this logarithm of the inverse of the chance. We will look at that more clearly later in a short while, and for now we consider that is the contribution of the ith event or the ith object to the entire system. Let's consider the simplest example of a random system that makes only two things. If the probability of the first thing or object to be P1 and that of the second to be P2, the entropy, the equation of the entropy becomes this summation of P1 log 1 over P1 and P2 log 1 over P2. To be more specific, the P1 is that we draw from this black box green ball, and let us the first event is to draw the green ball, and the probability of this first event P1 to be 1 out of 12, and the probability of P2 is to draw this red ball to be 11 out of 12 times. To compute the entropy of this system, we substitute the quantities using these specific numbers and get this result. Look at the logarithm of the inverse probability. For the event or object with a small chance of happening, the inverse of its probability is large. If we want to consider it in an intuitive way, we can think that this is a small beast but shouts very loud. So for the green ball, it only has the chance 1 out of 12 times to come out, and the inverse of the probability is 12. Take the logarithm is 2.48 something. And for the large guy, it is calm, if you think that intuitively. And actually, the chance of joining the red ball is close to 1. So the inverse of its probability is a little over 1, and the logarithm of it is close to 0. It is small. Put all this together, we got the entropy of this system is 0.28 something. Now consider another example with the same setting of the system, but now the two events, each of them has half of the probability of coming out. Now if we consider entropy, that is 0.69. Obviously, the entropy of 0.28 is less than 0.69. Let us consider the two systems in an alternative way. In the first one, we can consider there are 12 balls, one is green, and 11 of them are red. And for the second system, there are 6 balls of either color out of the 12 balls. And it is natural to see that the first system, that is the system shown by the left-hand side figure, is the color of the balls is purer than that of the second system, that on the right-hand side. So if the purity of the system is inversely connected to the entropy, and we can see that entropy mirrors the impurity of a system. For the two-object system, we can consider the system if the system is completely certain that, for example, in this figure, let x be the chance of one object in the two-object system. Obviously, 1 minus x will be the chance of the other object. When x is 0 or 1, that means the system is certain without any randomness in that. The entropy, it turns out to be 0 and takes its minimum possible value. When the chance of both events are equal to 0.5, the entropy takes its maximum value. And okay, here is a demonstration that entropy mirrors the impurity of at least this two-object system. Back to our decision tree construction problem. When we examine an attribute, we consider the entropy of the examples in our hands prior to adding any nodes to the trees. That is the entropy of S, and S is the number of training examples to begin with. The information gain is computed as the entropy of S minus the weighted sum of the entropy of the subtrees. And the subtrees are, of course, constructed by examining the value of the particular attribute. The difference between this entropy of the entire system before and the weighted sum of the entropy of those individual subtrees is the gain of information we obtained from testing that particular attribute. Here is a concrete example. If we have 14 samples In the previous example of the weather conditions and the playing of the game, that there are 9 positive examples and 5 negative examples. Perhaps there is no in this dataset the entropy of this two object or system is 0.94 prior to adding any attribute to the tree. Now if we test the attribute of humidity, we will end up with 2 subtrees. In the first subtree, we will have 7 examples. 3 of them are positive ones and 4 of them are negative ones, and the entropy of that subtree is 0.985. On the other hand, if the humidity is normal, we will have another subtree that also has 7 examples. But now 6 of the examples are positive and 1 of the example is negative. It has a smaller entropy, that is 0.592. After testing the humidity, the 2 subtrees have their respective entropy determined, and each of the system has 7 out of 14 examples. So the weight to each of the subtree is 0.5, and let's follow the equation of the information gain, and we can compute the gain of the information by testing the attribute of humidity is 0.940 minus the weighted sum of the left and right trees entropy together, and the information gain is 0.151. Following the same procedure, we can arrive the conclusion that if instead now we test the attribute of wind, we'll end up with an information gain of 0.048. That is the gain smaller than the gain of testing humidity. So at this step, we choose to test humidity over testing the attribute of wind. Apart from entropy and information gain, there are other measurements of impurity. In the lab session, I would like you to try the Guinea impunity to test in the decision trees. And also you may want to check using experiment how the impurity measure affects the performance of the algorithm. And now let's have a look at the decision trees in the learning framework. Remember the models we have learned, like perception and the neural networks, are all having some parameters with the model, which is to be used to combine with the attributes of the data. For example, if the data is in a plane that is r to the power of 2, the hypothesis space of those parameter models, you can think they make some classification boundaries in the R2 space. Especially for perception, the classification boundary is a linear one. For neural network, it's more complex, but it is parametrized. That means to be controlled by those parameters of the model, and can be changed continuously to form maybe complex patterns on the surface, on the two-dimensional plane. On the other hand, for decision tree, the hypothesis space is fundamentally different from those parametric models. The classification boundaries of decision trees looks in a more rectangular form. That is because when we construct decision trees, when the decision tree is at working, it examines each the attribute of the data one by one. For each attribute, it makes a card, a card of the data space along with that dimension, or along the, or with respect to the values of that attribute, which is a dimension of the space. Therefore, when decision trees are cutting spaces, they always cut along those dimensions and result in those rectangular-like boundaries. The algorithm of building decision trees is actually perform a search in the hypothesis space. The search is from simple to complex. At the beginning, we have all samples attributed to one class without any separation. Obviously, there will be a lot of errors in this hypothesis space. And then decision tree building algorithm begins to add attribute testing rules to the trees. When add a rule, it add a cut of the data space along one dimension. And in each of the step, it only takes the current tree and add another cut to add another attribute to test to the tree. That means to add another cut to the current cut of the space. In its basic form, all those algorithm doesn't do backtracking. That means in a later stage, if you find the cutting or the testing of one attribute turns to be not as optimal as it looked when we test the attribute, we have no chance to go back and change another attribute to test in the previous step. With this attribute, the search algorithm of decision trees is a greedy search algorithm. That means it almost always arrived in some local optimal in the decision tree hypothesis space. And the variance of such, in technical terms, the variance of such algorithms is high.